All right, so now we need to talk about the loops of Henle. So the loops of Henle, we know we got the descending and the ascending loops of Henle. And filtrate comes into the proximal convoluted tubule here. From the capsule, and then it goes down the descending loop and then back up the ascending loop to get to the distal convoluted tubule. All right, so when we're looking at the the loop, it's in the medulla. Most of it is in the medulla. So we know that out here is the cortex, and then in here is the medulla. And in the descending loop, so in the descending loop of Henle, the filtrate goes in there, and when it goes in there, the walls of that loop, that part of the loop, are only permeable to water. Permeable to water, they are not permeable to solutes. So as the filtrate comes down here, the water is going to leave. Okay? Because it can, all right? And there's a reason for it. After the hairpin turn, the filtrate gets down here, it's losing water, it turns and comes up, and since it hasn't lost any solutes because it's not permeable to solutes, it goes into the ascending loop of Henle. And in the ascending loop of Henle, it is impermeable to water. And what it does is it has like pumps on it, and it actively pumps out solutes, mostly sodium. Okay, so other ions too, but mostly sodium. So as it goes into the ascending loop, we've got these little pumps on here, and it's pumping out the solutes. Okay, it's keeping the water, so it's pumping out the solutes. So as the filtrate is going down the descending loop, it's losing water, it can't move any solutes, so its osmolarity is going up. Okay, it's going up because it's accumulating solutes. And then as it makes the hairpin turn, the osmolarity is like really, really high in the filtrate. And as it makes the hairpin turn, it comes up here, we start pumping out those solutes, and the osmolarity goes back up, or goes back down, sorry. Okay, so it gets more dilute. So it gets really concentrated going down, and then less and less concentrated as it goes back up. All right, so what does that mean exactly? Well, let's see. So osmolarity is the concentration of a solution and it's expressed in milliosmoles. So osmoles per liter. Okay. So in the cortex, where the glomerulus is and the Bowman's capsule, proximal convoluted tubule, and then of course the interstitial fluid and area around it, the osmolarity is about 300. It's like 270, but we'll round it up to 300. And the osmolarity is isoosmotic in all of these areas. So it's, let's say it's 300 in the vessels. So 300 here. It's also 300 here, and it's 300 here. So it is isoosmotic. Okay, so in the cortex, it remains, the whole area remains at 300 isoosmotic. Okay, so as it goes down into the medulla, it's going down at an osmolarity of 300. Okay, the concentration of the loops of Henle, because of this pumping and this water coming out on this side and pumping of solutes on the other side, the concentration of the loop going down into the medulla is changing. Okay, so the concentration of the medulla is changing, it's increasing as we go down. So it's getting more and more concentrated and very, very salty. It's very salty here. Okay, I mean, we're getting a bunch of sodium pumped out of here and other ions. So it's a very salty area. And the further you go down, the saltier it gets. Okay, so so it's 300 here. It ends up as we go down, it gets saltier and saltier and saltier and saltier and saltier. And then once we're at the bottom of the loop of Henle, we're at about 1200 milliosmoles. And then we take the hairpin turn, come back up, and then we start getting less and less concentrated again as we're going back up. Okay, so how does this occur? This change in osmolarity as we go down the medulla is caused by something called the countercurrent multiplier. So as this filtrate goes down into the loop is basically there to alter the concentration of what we're going to have as urine. Okay, so either it's going to be, really concentrated or really dilute or somewhere there in the middle. And this is where that basically occurs. So basically, this 300 milliosmol filtrate flows down into this weird salty environment. So as it goes into the descending loop, the solutes can't go anywhere, okay? And so since the interstitial fluid is more concentrated than the filtrate, water is going to follow the solute and go out into the interstitial space. and it's going to want to try to equalize that. So as the 300 gets down into where it's 400, water's going to leave until it's equal, either 400 and 400, 300 and 300, 350 and 350, whatever it is. But over here on this other side, where filtrate's moving in through the ascending loop, we've got pumping of solutes into this interstitial space. So the body, the kidney itself in this area says, okay, we have to be concentrated here. We have to be able to manipulate the filtrate down here, or we're not going to get anything filtered or anything. Nothing's going to happen if it's isoosmotic. Nothing's going to happen here. So the kidney pumps out solutes here, making sure there is a difference between the filtrate and the interstitial space of about 200 milliosmoles. So as the filtrate's coming down, water is coming out and it's becoming equal. Solutes are being pumped out to get it back unequal, to make sure that the concentration of the interstitial space is higher than what it is in the filtrate. So it pumps out, it makes it 200. Okay, so now we get down to 500. So now let's say it equalized to 300 when it went into the 400. So now we pumped out solutes, so now it's 500 in the interstitial space. So 500 to 300. Okay, well, more water comes out and makes it equal at 500 or 400. All right, so we pump out more solutes over here and we make it to 600, so that there's a difference between 200, 400 to 600. More water comes out. It becomes equal again to 500. Pumping out some solutes. Now we make it 700. There's the 200 difference again. Water comes out. It keeps doing this over and over and over until we get down to 1200 milliosmoles. That's at the end of the loop, and then we start going up, and then the concentration of the filtrate that's there starts to get more and more diluted. As in this side of the loop, you've got solutes being pumped out, but water can't go anywhere because it's impermeable to water. Okay, so that pumping out of solutes and water coming out of the descending, that's called the countercurrent multiplier, and it is creating this weird salty gradient of concentrated fluid in the medulla. Okay, and the fact that the loop is in there is allowing, we're allowing this to happen, and it's adjusting what's ultimately will be the urine. Okay, so if we go in here at 300, the filtrate's going to get more and more and more concentrated. It's going to become, 400 and then 600 and then 800 and so on till we get down to here to 1200, and then it's going to go back and it's going to go down again. 900, 700, whatever, until up here, as it makes its little turn into the proximal or the distal convoluted tubule, it could be as low as 100 milliosmoles. Okay, it could be a range, but it's going to be way more dilute. Okay, once we get to the distal convoluted tubule, so in the distal convoluted tubule and the collecting duct, so the D, use a different color, but okay. So once we get to the DCT and collecting duct, then these two tubes are affected by hormones. And those hormones are what maintain electrolyte and fluid balance. So we're going to see hormones like ADH, antidiuretic hormone, aldosterone. Any of these hormones target the distal convoluted tubule and the collecting duct to basically fine-tune the urine. So we'll put fine-tune urine's concentration. Okay. All right, so I know that that's confusing. So I am going to post on Blackboard a video that shows this in action and makes it much easier to understand. All right, so looking at this, there's another sort of part of this story, okay? So here's the countercurrent multiplier. This is how we're getting our dilute urine as we get to the distal convoluted tubules through this crazy countercurrent multiplier concentration salty blah 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 thing going on in the medulla. Well, there's one thing that we haven't taken into consideration in this picture, and that's the blood. Because why does it just go to 1200 and then go back up? I mean, why does it just not continue to just get saltier and saltier and saltier and the numbers just keep going? Well, there's a reason for that. Remember that the blood supply, so we have the efferent arteriole that's taking blood out of the glomerulus, and it's sending that into the peritubular capillaries. And those peritubular capillaries are wrapped around the proximal convoluted tubule and the distal convoluted tubule. In the proximal convoluted, that's where the 70% absorption is occurring, is into those peritubular capillaries. But ultimately, those capillaries go down into the medulla as well. And we showed this when we did the anatomy here. So here's the vessels. And again, this isn't one vessel. It's, that vasorecta basically thing. Okay. So this blood here is also affected by the gradient here. Up here in the cortex, it's 300. It's isoosmotic with everything else. But as it goes, remember, it's traveling in this direction, which is opposite of the filtrate, and it's going into this crazy gradient thing, all right? So as it's coming down here, the blood itself is getting more and more concentrated, okay? So it's getting really concentrated over here, and the reason why is it's taking up some of these ions that are being pumped out. So some of these solutes are going into the blood. It's picking them up. The rest of it is going out into the interstitial space, but some of it's being picked up here by the blood, and that's why the blood is getting more concentrated. It makes a hairpin turn, and now it's starting to pick up water because water's coming out of here, and now we're getting water. So now the concentration is now decreasing again. So by the time it's back up in the cortex, it's back to 300. This is called the countercurrent exchanger. Okay, because it's exchanging some of these solutes in the water to go back into the blood rather than just be in the interstitial space. All right, so I know that's long and confusing, but again, I'll put on another video on here that will help make it more clear because it'll be more of a live action moving thing.